Okay, let's dive in. We've got a few really interesting sources here. The main research paper, a briefing doc, a study guide, all about this thing called SCONE. And if you're involved with large language models, this constant push and pull, right? We want them smarter, knowing more stuff, handling really specific language. But that usually means bigger models. And bigger models, well, they get expensive and slow to actually use. It's a real bottleneck, especially right at the front door, where the model first sees the text you give it.
Yeah, that's the input embedding layer. It's basically the translator, turning our words, our tokens, into numbers the neural network gets. And SCONE, well, it's this really academically interesting contribution, a novel way to tackle scaling right there on the input side. It sort of unlocks this huge potential without the usual massive costs when you actually run the model during inference.
Okay, so that's our mission for this deep dive. Really unpack the technical side of SCONE. What is it? How does it work its magic? And why is it actually a big step forward compared to how things were done before? What does it mean for you if you're building or using LLMs? Think of this as getting you right up to speed on this specific bit of research. So let's start with the problem SCONE tackles. The input embedding layer. Fundamentally, it's just a big lookup table, right? Word in, vector out.
Exactly. A dictionary, essentially. And if you want the model to grasp more nuances, maybe specific names, technical terms, longer phrases, the obvious thought is, okay, let's just make the dictionary bigger. Add millions of words or parts of words, give it more input detail. But like the sources point out, this old way runs into, well, two pretty big roadblocks.
And the first one's structural, isn't it? It's about how these models are usually put together, something about the output layer.
Precisely. The tied output layer, it's a common design choice, mostly for efficiency. See, the part of the model that predicts the next word, the part that has to figure out the probability for every single possible word it could say next, it usually shares the exact same huge list of words, the same matrix, as the input layer. Now, imagine you expanded that list to millions of words for the input.
Oh, I see.
Yeah, so every time the model generates one word, it has to calculate a probability for all million possibilities on the output side. The sources call this the decoding cost, and it just balloons. It becomes impractical, as the paper says, way sooner than you'd think. They even mentioned some GPT-2 tests where performance actually got worse with these super large vocabularies. It's like, yeah, too much choice slows everything down.
Wow, yeah, millions of checks for every single word generated. That sounds incredibly expensive. Okay, so that's the prediction cost problem. What's the second issue?
That's about training. It's the tail tokens and sparse updates problem. In any real text, some words are super common, but most words are actually pretty rare. These are the tail tokens. When you train a standard embedding table, the model learns by updating the vector for each word it sees. But if you have a giant vocabulary, most of those words are tail tokens. They just don't show up often enough in the training data.
So they don't get updated much.
Exactly. The sources have this striking stat. Train on 100 million tokens with a 2 million word vocabulary. Only about 7% of those words get updated more than 100 times. But with a standard, smaller 32,000 word vocabulary, almost 98% get over 100 updates. So for all those rare words you added, their embeddings are barely trained. They're kind of low quality, almost useless vectors.
Okay, got it. So just making the word list bigger seems like the simple fix for better input, but it backfires spectacularly. It makes predictions incredibly slow and expensive because of the tied output layer. And the new words you added end up with terrible undertrained embeddings anyway because they're too rare. Clearly need a different plan.
And that's precisely where SCONE comes in with its technical contribution. The core idea isn't just adding more tokens to that main vocabulary. Instead, it augments the standard token embeddings with embeddings for frequent n-grams, sequences of words. They call them f-grams. Think like machine learning or natural language processing, these common phrases. And the first really key innovation, academically speaking, is that this set of f-grams, it's kept totally separate. It's decoupled from the main token vocabulary.
Decoupled.
Yes. And crucially, it's decoupled from the size of that output prediction layer we talked about. This means you could potentially have, billions of these f-grams without making that prediction step explode.
Okay, that solves the prediction cost problem. Smart. But how do you get good embeddings for all these billions of potential f-grams? Wouldn't you just end up with another massive table that has the same sparse update problem, all those rare phrases?
Right, that's the potential pitfall. And that leads to SCONE's second major innovation. Instead of trying to train another huge static lookup table directly, which, would be sparse and also hog accelerator memory during training, SCONE uses a separate kind of helper neural network during the training phase. They call it the FGRAM model, or MathCal. What this network does is it learns to dynamically generate an embedding for an FGRAM on the fly. It looks at the individual token embeddings that make up the FGRAM and computes a combined contextualized embedding for the whole sequence. And it happens jointly while the main language model is also being trained.
Ah, okay. So during training, it's not looking things up in a giant FGRAM table. It's calculating them using this extra little network. That avoids this sparse table issue during training. Clever. But wait, if you have to run this extra Lana MathCal network every time you see an FGRAM during inference when you're actually using the model, wouldn't that slow things down? Add extra computation.
And that brings us to the third key innovation, the real deployment magic, you could say, the offloading. Once the training is all done and the MathCal model has learned how to generate good FGRAM embeddings, they basically pre-compute the outputs of MathCal text for all the selected clams, just run everything through at once. This creates that massive static lookup table we talked about, the FGRAM embedding layer. They call it MathCal, but here's the breakthrough. This huge table, they offload. They move it off the expensive fast accelerator memory, the GPU or TPU memory, and put it onto cheaper, much larger capacity storage, like your main system RAM, or even faster NVMe SSDs.
Whoa, okay, off the accelerator entirely.
Entirely off the accelerator for inference. So when the model is running, instead of calculating the FGRAM embedding dynamically, it just does a quick lookup in this giant pre-computed table stored in RAM or on the SSD. And the sources are clear. This lookup is fast. It has minimal impact on latency.
Okay, let me see if I've got this. It's quite elegant. Training uses this extra neural net MathCals to learn how to generate FGRAM embeddings dynamically. This avoids sparse updates and keeps training memory use down. Then for inference, you ditch the generator network. You pre-compute all its possible outputs into a giant table, MathCals, and you stick that table in cheaper RAM or SSD storage off the main accelerator. Lookups are fast enough, prediction cost isn't affected. That neatly sidesteps both the prediction cost issue and the sparse update issue and the accelerator memory bottleneck at inference. That's really clever.
Exactly. It decouples learning from lookup, and it smartly uses different memory tiers. And this whole setup, the decoupling, the dynamic training generation, the static inference lookup, the offloading it, unlocks totally new ways to scale these models. Ways that just weren't feasible before, specifically because they keep the inference cost. And really importantly, the accelerator memory usage during inference fixed. Keeping that accelerator footprint flat is a major academic point and a huge practical win.
New scaling dimensions. Beyond just making the main model bigger, tell me more.
Right. The first new dimension is simply scaling the number of FGRAMs, making that offload table MathCal bigger. You can improve the model just by adding embeddings for more frequent phrases. The paper shows this clearly, figure 4. As they increase the FGRAM count from about 500,000 up to 100 million, performance gets consistently better. This costs more RAM or FSD space, sure, but the expense of accelerator, its inference load stays the same.
Okay, so more cheap memory equals better model without touching the GPU VRAM at inference. What's the second dimension?
The second is scaling the size of the MathCal model itself. The helper network used only during training, you can make that network bigger, more powerful. Figure 6 in the paper shows that as MathCal text gets larger relative to the main model, say, going from half the size to 3 times the size, the final model's performance, perplexity, improves. Now, this does cost more compute during training. But again, because MathCal A is thrown away before inference and replaced by the static MathCal table, it adds 0 extra cost or resource usage on the accelerator during inference time.
Wow, okay, that really is a different way to think about scaling. Normally, bigger model means bigger inference cost, period. More expensive GPUs needed when you actually run it. But SCONE gives you these levers. Spend more on training by beefing up MathCal text, or use more cheap off-accelerator storage by adding FGRAMs. And you get a better model without needing more accelerator power at inference. That feels like a fundamental shift, breaking that direct link.
It really is. It provides a way to improve the model's capability, its knowledge, without necessarily growing the most expensive part of the equation when you deploy it.
So practically, how do they decide which n-grams become f-grams? I mean, there must be trillions of possible word sequences.
Yeah, they need a sensible way to pick. The sources cover this section 3.1. It's actually quite straightforward, sort of inspired by how BPE tokenization works. They just scan through their huge training data set and count how often different sequences of words, n-grams, appear up to a certain length, k.
How long?
They found k equals 5, so sequences up to 5 words long was generally enough. Longer ones just got too rare to be statistically useful, apparently. Then they just rank all the frequent sequences they found by how often they occurred and pick the top n, where n is however many f-grams they want in their set. Could be millions, could be billions.
So it's basically the most common short phrases that aren't already single tokens. Makes sense. But even millions, let alone a billion f-grams, that sounds like a massive lookup table, mathscal. How much memory are we talking? And crucially, is it really fast enough to pull data from RAM or an SSD during inference without causing a major slowdown?
They dug into exactly that, the practicalities. Section 4.3, Table 2, Figure 7. Space-wise, it scales linearly, as you'd expect. About 10 million of VAMs takes roughly 40 gigs of RAM, or maybe closer to 80 gigs on an NVMe drive. Scaling that up to a billion epigrams needs around 7.6 terabytes on NVMe. That's definitely doable with modern SSDs, but way too big for typical super RAM.
Terabytes, okay. But the cost difference is huge compared to accelerator memory, right?
Oh, absolutely. RAM is maybe, $2 a gig? NVMe is pennies, like $0.10 a gig. Accelerator memory, HBM, is vastly more expensive per gigabyte, so the trade-off makes sense financially. And then latency, the speed question, this is critical. The results show it's fast enough. Even pulling from NVMe, they found the lookup latency was well under the typical time budget per token for LLM inference, which they figure is around 10 milliseconds. With decent batch sizes, like 16, they were seeing sub-millisecond latency. And if the table fits in RAM, they said the impact on overall throughput was negligible.
Okay, that's the key validation, really. The concept is neat, but if the offloading made inference crawl, it wouldn't matter. But it seems they've shown it's practically feasible and fast enough. That makes it truly useful.
Yes, the engineering side holds up, which is crucial for making the academic innovation impactful.
So the big question, how did models trained with SCONE actually perform against standard models? What were the results?
They ran large-scale tests using the OLMO framework. Section 4.2, Table 1 lays it out, and the headline result is pretty compelling. They state, a SCONE model with 1B accelerator-resident parameters outperforms a 1.9B baseline that requires approximately 2 post-more inference, FLOPs, and accelerator memory.
Wait, say that again. A 1 billion parameter SCONE model beats a nearly 2 billion parameter standard model.
Yep, outperforms it slightly in terms of accuracy or perplexity.
While needing half the inference compute and memory.
Exactly. About 48% less inference flops and accelerator memory, to be precise, for that comparison using 1 billion f-grams.
That is wow. That's a massive efficiency win.
It's significant. They also showed a smaller SCONE setup, a 1.3 billion parameter model with just 10 million f-grams, achieved basically the same accuracy as the 1.9 billion baseline, but still used 32% less inference flops and memory.
So you can get parity with a much smaller inference footprint, or even beat a larger model with roughly half the resources. That's impressive evidence. How does this stack up against other clever ideas people are using to make LLMs more efficient? Things like mixture of experts.
Good question. The paper compares SCONE to a few related approaches. One is the over-tokenized transformer. Similar idea, using n-grams at the input, but they train the n-gram embeddings more directly. SCONE seemed to get better gains, which the authors think is because SCONE's separate mathogram network adds more learning capacity during training. Also, that over-tokenized method apparently still needed its extra embedding stuff on the accelerator during training, which SCONE avoids.
Okay, so maybe a bit more powerful due to the training setup. What about MOMI?
Right, mixture of experts, OV, and also things like memory layers. Those also try to keep the compute cost per token fixed by only using parts of the model at a time. But SCONE makes a key distinction, especially in Appendix B. While Mo fixes flops, it usually needs all the expert models loaded into accelerator memory. Memory lands also need their stored embeddings on the accelerator. SCONE is unique, they argue, because it fixes the accelerator memory footprint by actually offloading that huge f-gram table. That's a different kind of efficiency gain.
So Mo saves compute but might still need lots of accelerator RAM, while SCONE specifically targets reducing that expensive RAM usage at inference.
Exactly. And one more comparison. Mixture of lookup experts. This sounds very similar trainable module replaced by a lookup table for inference. It was concurrent work. SCONE's authors suggest their approach offers an additional innovation, the ability to scale the number of keys, the f-grams themselves, much more effectively, allowing for those massive terabyte-scale lookup tables if needed, really maximizing the benefit from the training.
Okay, so SCONE seems to carve out its own niche. It's not just another way to activate parts of a model. It's fundamentally changing where the input information is stored and accessed during inference, specifically to minimize the load on the most expensive hardware component. That feels like a distinct contribution.
I think that's a fair summary. It adds a new tool, a new scaling dimension, focused on the input layer and leveraging memory hierarchy in a novel way.
So let's bring it back to the practical level. Why should you, listening to this, care about SCONE beyond the academic elegance?
Well, it hits right at some major pain points in using LLMs today. First, serving costs. Running these models, especially at scale with billions of queries, costs a lot, mainly due to the expensive accelerators needed for inference. SCONE directly reduces the need for accelerator memory and compute for a given level of performance. That means potentially much lower operational costs.
Cheaper to run the same quality model, basically.
Right. Second, latency. For things like chatbots or real-time assistants, speed matters. SCONE lets you use these richer, more knowledgeable models, potentially, without adding extra delay per word generated because that offloaded lookup is so fast.
So better models without the speed penalty.
Potentially, yes. And third, it could enable a deployment on less powerful hardware. If a SCONE model performs like a much larger baseline but fits in less accelerator VRAM, maybe you can run it effectively on cheaper GPUs or edge devices where the bigger models simply wouldn't fit.
That opens up possibilities. It definitely sounds like a powerful new option in the toolbox for building and deploying LLMs.
I think so. To sum it up, SCONE offers this scalable way to add rich, contextual fries embeddings. Its real trick is decoupling training needs from inference needs by using that dynamic generator mathkill for inference and then swapping to a static offloaded lookup table for inference. This fixes the accelerator memory footprint during inference, which is a major bottleneck, offering significant potential for cost savings and efficiency gains.
Thinking ahead, the paper briefly mentions future work, maybe applying this offloading idea to even longer, more complex things than just short n-grams. They touch on the challenge. What's the right key to look up? Maybe not just the text itself, but some kind of semantic meaning. It makes you wonder, could the input embedding layer, which we usually think of as pretty simple, become this much more complex, dynamic part of a model? Almost like an external memory, it can query cheaply during inference. Definitely something interesting to think about, how these architectures might continue to evolve. Well, this has been a fascinating look under the hood of SCONE. Thanks for joining us for this deep dive.